postdoc seminar. Our speaker today is Ghosh, and he's a postdoc in NCTS. And so for this talk, there's a recording, so please be aware that you're recorded. Okay, so I'll let the speaker introduce his own title.
Well, thank you for inviting me to the Taipei postdoc seminar, and I'm very delighted. I worked hard preparing the slides. And so I'm going to talk about G2 and spin 7 geometry and some applications in M theory / F theory compactification. So it will be a very elementary talk. There will be aspects of differential geometry, algebraic geometry, physics, but all of them are at a very elementary level. And so do not expect some like you will see them on the slides, but do not expect some research level results. But it is kind of setting the ground for me to talk about what I'm gonna work on at NCTS in the next couple of years. So this is the outline. It's a mixture of, as I said, a lot of different ideas. There will be a lot of definitions, starting from the very elementary ones. If you already know them, perfect. If you don't know them, don't be bogged down by all the technical definition and stuff. Just try to get the story. In fact, I'm not gonna read out the slides either. I'm gonna gist it for you guys. So let's start with some review of Riemannian geometry for those who need a very quick crash course. So I'll start with my n-dimensional smooth manifold with a Riemannian metric. So that means a positive definite symmetric bilinear form. At each point P, I can associate an n-dimensional vector space, which is the tangent space, or the dimension of that vector space is the same as the manifold. I mean, that comes from the definition. I'll consider the tangent bundle. And then there's this notion of affine connection. So if I give you two vector fields, that means section of your bundle. And then, so x and y, you can think of nabla xy to be some sort of directional derivative of y in the direction of x. And this is some obvious relations that it should satisfy. It's a derivation. You can see the Leibniz rule satisfying its derivative. So now, a Levi-Civita connection is something more than an affine connection. It has to be compatible with the metric. It has to be torsion-free. So this relation, oops. Oh, sorry. Full screen. What's this full screen? Ooh. Oh, now it's, oh no. Okay, got it. Perfect. Right. So a Levi-Civita connection is something more. So look at this relation. This one. It's a very important one. It will come up again and again. So the compatibility up with the metric. So that's the Levi-Civita connection on defined on your tangent bundle. Now there's a natural notion of parallel transport, which is basically if you should be able to transport a tangent vector along your manifold from one point to another. So that means you should have some sort of parallel transport operator from one tangent space to another. So the idea is you will start with a curve where the initial point is P and final point is Q. And then for a vector on your tangent space, you should be able to find a unique vector field, which is a section of the pullback bundle, such that the Levi-Civita connection of that section in the direction of the tangent or of the curve is 0. So basically what's happening, if you start with a tangent vector and you kind of move along your manifold. That's basically a parallel transport. And now what I'm going to do, I'm going to consider a loop. So my final point, initial point and final point is the same. And then basically you can start from the initial point and come back to it. And then it's invertible. You can go back. Right. So it is an invertible linear map, which means that map is an element of the general linear group. And so if it's an invertible linear map, the set of all these parallel transports along the loop will give you a group. And that group is called a holonomy, is the holonomy group. And clearly you can see that's a subgroup of the general linear group. Now you can prove that this is independent of the base point. So compare with how you define like first fundamental group, right? It's a very similar kind of idea. So now that's the holonomy group and of your metric. And remember, your metric and your Levi-Civita connection are compatible with each other. Now it is clearly a least subgroup of your general linear group. And if well, usually you'll see the examples. Well, so again, you will see these groups are very, I'll show you exactly what these groups are. For example, you'll see the groups like SON, SUN, these are precisely the holonomy groups. Okay, so as I said, you start, you move along your manifold and come back. Now, because of the geometry of your manifold, what will happen if you start here, go around, come back, you will see that's a deviation. It won't coincide depending on the geometry of your manifold. And that's precisely because of the curvature of your space, of your manifold. So the holonomy group, rather the idea of a parallel transport, give rise to the notion of curvature. So of course, this is the classic Riemann curvature tensor, which you can think of as the Lie algebra of holonomy group tensor with the space of two forms. And this is the expression everybody kind of have seen in the Riemannian geometry. And in a local orthonormal frame of your tangent space, it should look like this. Now, if you take the trace, then you get something called a Ricci tensor or Ricci curvature. So again, looks like this. You take trace further and then you get scalar curvature. So I just mentioned the holonomy groups, right? And I promised examples or so if you start with a Riemannian manifold, which is simply connected, oriented, non-locally symmetric and irreducible, if you don't know what they mean, you don't need to worry about that. Then Beje, he classified all the holonomy groups for Riemannian manifolds. And turned out there's a notion of holonomy reduction, which means it will be a subgroup of your general linear group. The more geometric structure you impose on your manifold, this group gets smaller and smaller and smaller. Now you can clearly see if your manifold is orientable, then already you have the special, so instead of GLNR, it will become SLNR. If you have the Riemannian metric, it's a Riemannian manifold, then you have the notion of orthonormality. Then this holonomy group will reduce further to SON. Now, if you have if your manifold is a Kähler manifold, then your holonomy group will be UN. If it's a Calabi-Yau, your holonomy group will be SUN, hyperkähler, SPN, quaternary Kähler, SPN dot SP1 dot means cross mod Z2, and then there are these holonomy groups G2 and spin 7. So that's the notion of holonomy reduction. Holonomy groups are basically precisely what kind of geometric structure your manifold has. Now, when we talk about the Riemannian manifold, SON, and now you can see the Keller and Calabi-Yau. There, so this list you can associate the normed division algebras to it. The Riemannian is the real field R. Keller and Calabi-Yau over the complex. Hyperkeller and quaternionic Keller over the quaternions. And the G2 and spin 7, they are related to the octonionic algebra. In fact, real complex quaternions, octonions are the only norm division algebras over R. So that controls this thing, and that ensures that you don't. This is the complete list, and so it turns out, other than the first one, all of the last 5 are Ricci flat. I defined the Ricci tensor. It will become 0, and all of them are spin manifolds. So let's talk about what are spin manifolds. So this is the start of spin geometry. First, I need to talk about Clifford algebras. So you start with a vector space over a field and consider a symmetric bilinear form. You can just think about Rn equipped with an inner product. Then the tensor algebra is precisely, you have the field, you direct sum with your vector space, you direct sum with vector space tensor, vector space, and continue. So that's your tensor algebra. Now we consider two-sided ideal generated by this. Now if you don't have this inner product, then if you take the quotient, it will give you the exterior algebra. Whereas here you have that inner product. So when you take the quotient, it gives you something called a Clifford algebra. So basically, Clifford product looks like this. And using polarization, you can define, so that's the defining relation, which is very famous. Okay, yeah. Right. So basically, PV quotient IV, that's what you're doing. Now, so that's the defining relation of your Clifford algebras. Now we consider an involution map. So alpha from V to V, where it changes the sign. So now you can clearly extend this map, involution map, to the whole Clifford algebra, where alpha of Clifford product of K elements is just Clifford product of alpha of that element. Now you can clearly see, if this number K is even, then there will be even number of minuses, they will cancel out, and you will left with the same thing. Whereas if this is odd, it will be negative of the whole thing. So basically, which means alpha square is 1, and the plus minus eigenvalue, plus minus 1 are the eigenvalues, and so it will give you a decomposition of your Clifford algebra into the Clifford 0 part and Clifford 1 part. So 0 part means Clifford product of even number of elements, 1 part means odd number of elements. So as I said before, just take your vector space to be Rn and take Q to be inner product. And this is the notation I'm gonna use from now on, CLN, to denote CLVQ, where V is Rn and Q is inner product. So let's define spin group. I have the group spin 7 in the title of my talk. So let's look at what spin group is. So spin group is basically Clifford product of even number of unit vectors. So if you consider the set of unit vectors, that's your sphere. If you consider the set of even number of Clifford products of unit vectors, that's your spin group. And clearly, since it's even number of it, belongs to the 0 part of the Clifford algebra. Now, this group is actually the universal double cover of your Lie group SON, which means if you consider the fundamental group, first fundamental group pi1 of spin 7, it will be 0. Definition of universal cover. Of course, n has to be greater than 3. And from this, you can clearly tell what the fundamental group of SON is. So that's an short exact sequence. And hmm? Right, spin n. Well, k varies from 2, 4 up to, it will go up to n. So you consider all those elements. Yeah. So when it reaches n, that's your volume form, right? So that's the maximum. Just like compare with like exterior products, wedge product. You can consider all smaller wedge products, but it will go up to the dimension of your manifold, and that's the volume form. Okay, yeah, I'm going a bit fast. So that's coming from the decomposition, CL0 into CL1. So CL0 means all the even number of products. Right. So these are some examples. It turns out spin 3 is just S3 and spin 4 is S3 cross S3. And then you have spin 5, spin 6, and so on and so forth. So now that you have a group, you have an algebra, you have Clifford algebra, you have spin group, the natural with, so the next thing would be talk about representations. So you can consider a K representation of your Clifford algebra, which is nothing but a K algebra homomorphism, where you have the Clifford module W. And then the action rho of phi, where phi is an element of Clifford algebra, acting on this an element of this module W, you can shorthand by phi dot W, and we call it the Clifford multiplication. Real or complex, that's what we'll take, K to be, real or complex. Of course, there are many other fields that people work with. For now and for physical purposes, these two are will consider K to be real or complex. So now you can clearly see you have the spin group inside the 0 part of the Clifford algebra. So you just restrict this representation to spin group, and you have what's called a spin representation. Now you can complexify your Clifford algebra. And then you can consider the complex representation. In fact, in practice, I almost always work with the complexification, the complex representation, and you call it the Dirac representation. Not a very popular term. Usually, everybody calls it spin representation or spinor representations. So let's consider an example. If you consider spin 4, then the spin representation is a 4-dimensional vector space. You can identify with C2 or even quaternions H. And an element of this vector space, we'll call it a spinor. So there's something called a spinor bundle. So you have seen tangent bundle. So tangent bundle, the fiber is your tangent space, which is a vector space of the same dimension as your manifold. And you know that it's Riemannian manifold. So you have a basis of that tangent space. And if you want to change your basis, preserving the orthonormality, basically you are acting by an SON, right? So and so you can actually think of your tangent space as the vector representation of SON. Whereas now you have the spinor representation. So you know that if SON lifts to spin n as a double cover, what you can do, you can think of a bundle where the fiber, instead of considering the vector representation of SON, you are going to consider it to be the spin representation of spin n. And that's your spinor bundle. Again, I'm putting a lot of things under the rug. The proper, construction basically comes from consider principal bundle and then consider an associated vector bundle. So don't worry about that. Just think of it informally like this for now, if you don't know it already. So if you can lift it globally, then we'll call the manifold a spin manifold, and of course you have the spinor bundle. You cannot always do that. It's very topological. The obstruction is topological. If you have seen characteristic classes, there's something called Stiefel-Whitney class, which is actually Z2 valued cohomology class. And the condition that a manifold is spin, or you can actually lift the SON to spin n globally and get a spinor bundle, is that your first and second Stiefel-Whitney class should vanish. And so now that I have you somehow know what a spin bundle is, and so now I'm going to talk about Dirac operators. So the Levi-Civita connection, you saw it defined, being defined on the tangent bundle. It says map from section of tangent bundle to a section of tangent bundle to section of tangent bundle. But now your tangent bundle lifts to the spinor bundle. So what will happen if your manifold is in this spin and you have the spinor bundle, your Levi-Civita connection will lift to a to here. Hmm. Well, same underlying manifold, but if the fiber is different, that means the bundle is different, because it is all vector bundle. Yeah, a different bundle, because yeah, it is still a vector bundle, but remember, tangent bundle is a special vector bundle where the fiber is your tangent space. Sometimes it stays the same, so it depends on what the dimension of your spin representation is. For example, for G2 and spin for G2 and spin 7, for G2 the dimension is the same. It's the dimension of the tangent bundle is 7, the dimension of so the fiber is also 7 for yeah. Mm. Mm. Yeah. Mm-hmm.
What does it mean for belief? Okay, you have like
Right. So we are not talking about representation to lift. We are talking about so SON has a natural lift to spin n, and then instead of considering the vector representation, which means SON acting on Rn or Cn, you are considering the spin representation, whereas spin n is acting on the spin module. So basically, instead of tangent, you replace the tangent bundle by your spin module. That's what you are doing. Hmm? Yes, yes. As you can see, it is a very special representation. So, for example, I gave the time example spin 4, right? There, the spin representation is C2, and the action is clearly you can see you can calculate it. So spin representation is a very particular representation with particular dimension. Again, as I said, because I am putting a lot of things under the rug, I have not defined them very rigorously, and also the same for the bundle. You can define it very rigorously. So basically, it's happening on a principal bundle level. If you have a principal bundle with SON fiber, then you can lift it to a spin N fiber bundle. And then instead of considering the associated vector bundle of that principal SON bundle with respect to the vector representation, you consider the associated vector bundle of your spin bundle with respect to the spin representation. That's what's happening. So if the topological obstruction is not there, then it will be global. Right. So now let's quickly talk about the Dirac operator. So as I said, my Levi-Civita connection will lift from the tangent bundle to the spinor bundle. And now I define the Dirac operator to be the Clifford product with the Levi-Civita connection, Clifford multiplication. So this is so basically you have this map. So the composition of your Levi-Civita connection with the Clifford multiplication is your Dirac operator. Now the volume form, that if you square that, so E1, E2 up to En, E1, E2 up to En, and then order it, you will see that gamma square is actually 1. So again, it means you have the eigenvalue plus minus 1, you have the eigenvalue decomposition of your spin representation as the positive part and the negative part, and that will decompose your spinor bundle as a plus and minus. Doesn't always happen. Your manifold has to be even dimensional, complex even dimensional. So then you will have this decomposition. Odd dimensional manifold, you will not see this decomposition. So basically, if you restrict your Dirac operator to the plus part and minus part, you can also define the positive and negative Dirac operators. Now, some terminology. You had the Levi-Civita connection. If you have a spinor, when acted on by Levi-Civita connection, it's 0. We'll call this spinor a parallel spinor. Whereas if it's 0 when it being acted on by the Dirac operator, and it's 0, then we'll call it a harmonic spinor. Now there's this very famous formula called Weissenbach formula or Lichnerovich formula, which says when you square it, it should give you the Laplacian plus the scalar curvature of over 4. So it's the geometry is already there. So the Laplacian is precisely the Laplacian for R3 it's minus del 2 del x2 minus del 2 del y2 minus del 2 del 2 the same thing plus the scalar curvature. So you can write the same thing if you have chiral Dirac operators as well. So now that you know the definition of your parallel spinor and harmonic spinor, you can clearly see if your manifold has zero scalar curvature, or rather zero Ricci curvature, which will imply zero scalar curvature, then these two are the same. Parallel spinors are harmonic spinors and vice versa. And suppose we denote the dimension of the space of parallel spinors, which considering your manifold is Ricci flat, is the same thing as linearly independent harmonic spinor. We denote that dimension to be n. Then there's this very famous theorem which calculates exactly how the exact dimension corresponding to your holonomic groups. And so I told you these if a manifold has these holonomic groups, Calabi-Yau, G2, spin 7, hyperkähler, then they're Ricci flat, and so these are the number of these are the dimensions of the parallel spinors, and that's directly related to supersymmetry. Let me be even more sketchy to talk about this because it will require a lot of notion of quantum mechanics and things like that. But basically, you can think of quantum field theory is being the study of Hilbert spaces, which has this decomposition into plus and minus. So this decomposition is because of this operator. Again, it has eigenvalue plus minus 1. So when so the states of the plus we'll call it bosonic state, and state of the H minus will call it the fermionic state. State means nothing but a vector in your Hilbert space, an element of your Hilbert space. So basically, bosonic particles mean particles with integer spin, and fermionic particles means particle with and like half spin, like half for electrons, 3/2, and so on and so forth. Now, the idea of supersymmetry is there should exist a symmetry between the bosonic particles and fermionic particles, and mathematically that means you should have something called a supersymmetry operator, which should if you give a bosonic state, it should give you a fermionic state. So basically, a map from H plus to H minus, and if you consider the conjugate, it will be H minus to H plus. So that's the operator, and you can. So your supersymmetry operator should clearly satisfy this relation. So that's just the commutator bracket, and so now in physics that there's a notion of Hamiltonian, which means basically energy. So you have so kinetic energy plus potential energy, and there's another thing called Lagrangian, which means kinetic energy minus potential energy, and they appear in symplectic geometry in Lagrangian and Hamiltonian subspaces, very similar notions. So now this Hamiltonian, which is energy, you can so there's these two relations. Q square should be 0, and the anti-commutator with Q and Q dagger should be twice the Hamiltonian. That's a relation, and it will generate an algebra, which is called the supersymmetry algebra. So physics has generated a lot of algebras like that. From supersymmetry, you have the supersymmetry algebra. From conformal field theory, you have the Virasoro algebra. From statistical mechanics, you have Temple-Lillie algebras and things like that. Basically, you start with a relation like that, and somehow they capture the physics. Right. So now we start with a fixed energy. So I said Hamiltonian is basically energy. And from the previous relation, you can see that energy equals 0 means when Q and Q dagger are acting on a state, it will be 0 from the second part of the relation, right? So H of psi equals 0 means Q dagger psi equals 0 and Q psi equals 0. So basically, it means the 0 mode of the operators Q and Q dagger are non-trivial. So 0 mode is somehow, I think, a bit more physicsy term for an element of the kernel. So those are eigenvectors or eigenstates with vanishing eigenvalues. So if that happens, if your system has 0 energy, then that supersymmetry is called an unbroken supersymmetry. In that case, the bosons and fermions have equal mass. On other hand, if it's non-zero, of course, that still has to be positive, then the equation 2 has no solution. Which means, in that case, the supersymmetry will be called spontaneously broken. So these are some terminology you will find in physics literature in the context of supersymmetry. But this second equation is definitely very interesting. It still talks about an element of the kernel. So now turns out you have the chiral Dirac operators, D plus and D minus. They are good candidates for your supersymmetry operator. They will satisfy the relations I told you about. Your scalar, you should start with 0 scalar coefficient, in particular 0 Ricci. It should be Ricci flat, and then you can clearly see the 0 modes of your Dirac operator are precisely the 0 modes of your Hamiltonian if your scalar curvature is 0. So basically now from Weizsäcker formula, you see that your Hamiltonian is 0 if and only if your psi is a parallel spinor. So then each parallel spinor, linearly independent, will give you a supersymmetry generator. Mm-hmm. Mm-hmm.
Okay, so we define directly the spinner.
Mm-hmm.
So just
Mm-hmm. Yeah. So, right. Suddenly here I wrote down spinor as an element of spin bundle, right? So it's not an element of so I have kind of abuse notation. It's a section of your spinor bundle. Yeah. Yeah, you can take it to be sections of the bundle. So yeah, in fact, that's the thing. Physics people rarely talks about bundles. In fact, all the physics papers you will just see Euclidean space, and then you will realize, well, they are just talking about nothing but a trivial bundle over Euclidean space. You know that. So yes, you are absolutely right. You can just think of that as a fiber of your bundle. So now, from my previous comment about supersymmetry operator generators are being your parallel spinners, so the dimension of your space of parallel spinners is precisely the number of linearly independent parallel spinners, which is the number of independent supersymmetry generators. And then going back to that Wang's theorem and that table of holonomic groups and a number of, so the dimension of the space of parallel spinners, you can clearly see that holonomic groups are in 1, 2. So for particular holonomic groups, you have particular number of supersymmetry generators. Now this is now I'll be very brief in talking about the compactification. So the idea, okay, so you have the supersymmetry algebra. And Nam, what he did, he looked at the representation of that algebra and studied it and had this conclusion that supersymmetry can only exist up to dimension 10. And there's something called supersymmetric gravity or supergravity that can only exist up to dimension 11. That's a monumental paper called Supersymmetry and Representation. So you should check it out. Wonderful paper. And so the idea of compactification of supersymmetric string theory, or later Witten came up with M theory to like unify like 5 different string theories. And then there's a new thing called F theory. So string theory is 10 dimensional, M theory 11 dimensional, F theory 12 dimensional. And the idea is you have your space time 4 dimensional Minkowski space, and your 10 dimensional, 11 dimensional, 12 dimensional theories are nothing but your space time times a compact manifold of dimension 6, 7, 8, which you already saw good candidates of it, Ricci flat manifolds, Calabi-Yau, G2, and spin 7, which you know to exist in dimension 6, 7, and 8. And yeah, so you have the Minkowski space. And going back to that Wang's theorem, now you have, in those theories, you have the holonomic groups, and then you compactify that that manifold with those holonomic groups, and you left with your space-time where the supersymmetry operator, the supersymmetry generators are precisely 1, 1, 2 coming from Calabi-Yau. Again, think about the chart, and here's 1. So here's something special happening. There's a flux which is reducing the number by 1 more. You don't need to worry about it. Just, the point of this is that correspondence and how it kind of contributes to the compactification. So the idea of basic idea of compactification is you define your physics in those dimensions 10, 11, 12. But when you compactify, the resulting thing, which is 4-dimensional, that physics should coincide with the already known physics. And that's where these manifolds come into play. And so I have been talking about Calabi-Yau G2 spin 7. So what are these manifolds? So let's quickly review these 3 manifolds. Calabi-Yau, that's relatively more well known. So basically you have all these conditions, they're the same, and if any of them happen, you call that manifold Calabi-Yau. So you start with a Kähler manifold, you look at the canonical line bundle, it's trivial, fantastic, you have Calabi-Yau. Same thing, you have a nowhere vanishing holomorphic N form. That's basically a section of that bundle, right? So fantastic, you have Calabi-Yau. It is a projective manifold, Calabi-Yau. Holonomic group SUN, Calabi-Yau. M is Ricci flat, again Calabi-Yau. So if you start with a Kähler manifold which is Ricci flat, it's a Calabi-Yau. And example, just start with your CPN complex projective space and consider non-singular hypersurface. You got Calabi-Yau. Or you can consider it, hypersurface of like something like a compact toric variety again. Oh, it's a submanifold of CPN. Okay, that comes from Yao's proof of Calabi's theorem. So it turns out there's a unique Kähler metric of CPN, which is the Fubini-Studi metric, and which is Ricci flat. So no, Fubini-Studi metric is not Ricci flat, but a submanifold of Calabi-Yau of CPN should be Ricci flat. Right. Yeah. Right. Yeah, this is one direction. You are right. I shouldn't have said, so I should remove that and I should say the others imply that. Yeah, there's, I think I made a mistake there. Well, I'll come back to that later. Yeah, I think that, yeah. No, it's projective algebraic. That makes sense, right? It's projective algebraic. Yeah, it's an implication, you are right. No, but the first and second one will imply. So remember, you already start with a Kähler manifold. Yeah. Yeah. Yeah, I start with a Kähler. That's the first thing. Yeah. Yeah, so if M is just some Riemannian manifold, and if then I talk about these conditions, they definitely won't mean Calabi-Yau. I already start with a Kähler, but you are right. I missed something in point 3. So forget about point 3 for now. Now, what's important is you start with the Kähler manifold, so you have a symplectic form in there, and from point 2, you have a nowhere vanishing holomorphic N form. So these two together, we'll call them the SUN structure. So having a Calabi-Yau implies having an SUN structure. And I'm going to define G2 and spin 7. Similarly, I'll talk about G2 structure and spin 7 structure by having the existence of some differential forms. So a G2 manifold, if I have a 3 form, which in local orthonormal basis can be written like that. So E1 to 7 means E1, wedge E2, wedge E7. That's a 3 form. So the reason it looks like that comes from, again, octonionic algebra. You write down the octonionic multiplication table, and then you kind of define things to be E1 dot E2 should give you E7. So this 3 form, the stabilizer group is your group G2. So that's where this G2 manifold G2 term comes into play. So further, you need some torsion free condition. The D of this 3 form should be 0, and then your manifold will be called a G2 manifold. Just think of that D phi equals 0, compared to your Kähler form to be closed and the holomorphic 2 form to be closed as well, and things like that. So now for spin 7, we'll do the same. I have a 4 form now, and I say that, well, D of that 4 form equals 0. That's the torsion free condition, and then your Riemannian manifold will be called a spin 7 manifold. Again, the stabilizer group of this 4 form is the Lie group spin 7, which I defined before. So that's the reason behind calling these manifolds G2 manifold or spin 7 manifold. I'll be very fast for this part. So you have the algebraic set, which is the common zero set of a subset of finite subset of your coordinate ring, and then if you consider irreducible algebraic set together with Zariski topology, you have the affine variety, you have the projective algebraic variety if it is an irreducible algebraic set of CPN. Open sets are called quasi. You have the rational map, which is the equivalent class of maps from the dense open set of dense set of X to Y, and where if they overlap in the intersection, we'll call it that's the equivalence relation. And then you have the birational map, which is it has a rational inverse. A point will be called non-singular if XOX is locally isomorphic to CK or CK near that point. Otherwise, it will be it will be singular. And a resolution is just you find a non-singular variety of your singular algebraic variety such that you have a proper birational map. So proper, I am gonna omit that part here, But basically, you construct X tilde, the resolution from your original variety by doing blow-ups. So think of like you have pointy things, you have balls, you attach those balls to remove the pointy things. That's the basic idea. And then you have these notions of like divisors, hypersurfaces, formal sums. And so you have the prime divisor, we'll call it exceptional if you have the map pi from X tilde to X, if pi E has at least codimension 2 in X. And then canonical divisor should satisfy this relation. You pull back the canonical bundle, and then you already have a canonical bundle, so they should satisfy. You should have this relation. So this last part are called discrepancies, and if AIs are positive, you have the canonical singularities. They're strictly positive. You have terminal singularities, and if they are all zero, which I like, which is we'll call the minimal resolution or Crepent resolution, then the canonical bundles are just pullback of one another. So examples. Now we are in a position to talk about examples. So nice examples of Calabi-Yau. You have K3 surface, which are basically again trivial canonical bundle with Hodge number 0. So Hodge number 10, it's just instead of you consider the Dolbeault cohomology and the Betti, that's the Betti number of Dolbeault cohomology. So now this is interesting. So I want to construct K3 surface, what's called Kumar construction. So basically you consider a lattice in C2, and then you quotient C2 by that lattice, basically you get a complex torus. Now you consider the antipodal map. So Z1, Z2 goes to minus Z1, minus Z2. And now this map has exactly 16 fixed points. You can clearly see. So now if you quotient your torus by this map, you get an orbifold, complex orbifold with exactly 16 singularities. So basically what you do, you blow up at those 16 points, and that's a Crepent resolution. And you get a K3 surface. But what's interesting here, since your torus is not algebraic, this K3 surface is not algebraic. So that's the Kumar construction. Now, so this work is by Dominic Joyce. So what he did, he needed to come up with compact examples of G2 and spin 7 manifold. And so he followed this Kumar construction. And so what he did, this is a perfect, harmony of algebraic and analytic / geometric techniques. He started with the 8 torus, T8, T7, typo. And so he chose a finite set acting on that torus that preserves that G2 structure and the metric. And then he took the quotient, which gave you an orbifold, and the fundamental group is finite. So that's important condition to have full holonomy. You don't want to come up with a like spin 7 manifold, but turns out it's a Calabi-Yau. So what's the point? We already have examples. We want non-trivial full holonomy examples. So now you take this gamma, this finite set very carefully, because we want the fundamental group to be finite. We want the resolution to be Krapent. And so basically turns out simple examples, like if you consider that gamma to be Z2 cube, that works. And then to resolve the singularity, there's in 4-dimensional, there's some 4-dimensional hyperkähler manifold called ALE spaces. They're related to something called gravitational instanton and things like that. So asymptotically local Euclidean means the metric is asymptotic to the Euclidean metric. And then you use that to resolve the singularities. And then the fundamental group of that will be finite, because you started with your original orbifold has finite fundamental group. So now you do a bit of analysis to take care of things. You are attaching something, the radii should match up and things like that. So that's what's happening here. And again, the same thing, you had an old G2 structure. Now after this, you have a new G2 structure. They should also satisfy some analytic restraint. And then you have a compact, smooth G2 manifold. So now what you do, you very carefully start considering different gamma, and you start getting a lot of examples of different G2 manifolds. So different means they all have different Betti numbers. That's how they're different. Now do the same for spin 7 manifolds. Instead of starting with the 7 torus T7, you start with 8 torus T8. Do the same thing, you will get compact examples of spin 7 manifolds. So now I want to just connect things a bit, and how these manifolds appear in compactification. So that was the work of Duff, Nielsen, and Pope, and they started with the 10-dimensional UV theory with one supersymmetry parameter, and they compactified a K3 surface, which gave them a 6-dimensional theory. Then they compactified K3 cross T2. That gave them the space-time, 4-dimensional space-time. And starting with 11 dimensions, the Joyce G2 manifolds, you compactify that, you end up with a 4-dimensional theory. It has one supersymmetry parameter. What about spin 7? Very little work has been done. In the context of compactification, compactifying Calabi-Yau 4-folds are more appealing because they have more supersymmetry parameters. Compactifying spin 7 manifolds in the context of M theory, which is the 11-dimensional theory, then you end up with something 3-dimensional, which doesn't have a supersymmetry parameters. It's not really interesting for physicists. Yeah. Basically, when you define no, remember, it's the 10-dimensional, 11-dimensional, 12-dimensional theory. The idea is you define physics in these dimensions, but ultimately you can think of that being your space-time times these compact manifolds, and which are have very small. Okay, technically it's compactification, but you are not actually compactifying it in the sense that going through a procedure. Basically, you are restricting it to the 4-dimensional part. So you are, it's a product manifold. So when you write down your physics for this product manifold, there's some physics happening on the compact 6-dimensional part. There's something happening on the 4-dimensional part, and so that's the basic idea. When you have a 10, 11, 12-dimensional theory, you write down the physics, and suddenly you split that theory into the 4-dimensional and 6-dimensional part, at least for the 10, and turns out the 4th dimensional part coincides with the known physics, and the 6th dimensional part, or the 7 and 8, whatever, there are some physics on the compact Calabi-Yau/G2/Spin7 manifold. So that's the idea of compactification. Again, I am being very sketchy with the physics here. You need to write down Lagrangians and then study the physical properties and things like that. Okay, so what about spin 7? I started talking about it. Turns out, well, in M theory, it's not very interesting for precisely for the reasons I mentioned, supersymmetry, generators, and things like that. For F theory, which is a new thing, Vapha is a very, and also Witten, it's the 12-dimensional theory. And if you compactify 8 dimension, you come up with 4-dimensional theory, and things, spin 7 manifolds are interesting there. However, there are some choices like they consider elliptic spin 7 manifold, which means you start with a 6-dimensional Calabi-Yau and you consider a bundle over it where the fibers are complex elliptic curves. However, not much things have been done on this. There are conjectures floating around. You start with a 6-dimensional Calabi-Yau, then consider a bundle over it. Yeah. So now, what's the problem starting the physics involving spin 7 compactification? The main problem is when Witten and others started looking at the G2 compactification. So you compactify 10, 11 dimensional theory by a G2 manifold. Somehow you need to know something about the metric on the moduli space of G2 structures. So you fix a manifold, you know that all the G2 structures on that manifold, okay, 7-dimensional manifold, you know that all the G2 structures are basically 4 forms which are closed. So 3 forms which are closed. So basically elements of your 3rd cohomology group. Now, the moduli space, again, work of Joyce, is the moduli space is actually an open subset of 3rd cohomology. And that means the moduli space is actually an affine manifold. So defining a Riemannian metric on an affine manifold is pretty easy. So you have a metric on the moduli space of G2 structures. Similar, Witten has worked on this, and many other people have worked on this, and it was originally written down by Hitchin. But for spin 7, the moduli space of spin 7 structures, which since spin 7 structures are 4 form and closed, they are elements of the 4th cohomology group. But the moduli space is actually a closed subspace of H4. And so it is not affine, which means all the techniques to define a metric, which was done in the G2 case, through something called like the Hessian. You define the Hessian and then you define the metric using that Hessian. That does not work here. So far, no one has really written down a metric on the moduli space of spin 7 manifolds, which is very important to do this. In fact, that's the project I'm working on right now. Trying to write down a metric on the moduli space of spin 7 manifolds, which will have direct implication in the compactification process. That's it.